Okay, welcome everybody. This is Steve Hamrick, Director of the Penn State Center for Acoustics and Vibration. And we're pleased to have you here for day 2 of the CAV workshop. And this is the International Liaisons session. And I'm always excited to have this because it's just great for all of us to get to know what's happening outside the US and outside of Penn State. And I'm just so grateful that 7 of our 8 international liaisons, even though they aren't able to visit us in person this year, have agreed to participate and pre-record some great videos, which I hope a lot of you have had a chance to watch, and are here with us today to give short updates, maybe in the order of 5 to 10 minutes each, and then take questions and perhaps have a nice discussion afterwards. A couple of folks are missing, but we'll see how that goes. Here was the intended ordering. And the reason we're starting with Randolph and Yonghua is because it's very late over in Asia, and we want them to go first. Then we'll shift over to the Europeans, and then Olivier from Sherbrooke in North America will go last. And if Goran hasn't joined us by the time it's his turn, we may just jump to Lars. Actually, Robert Meyer is going to fill in for Lars, and then Filippo, and then give Goran a chance to get on. And if that doesn't work, then we'll pick on some of our other friends from Incident Lyon to perhaps take his place. So, Randolph, if you're online, if you would go next. And you should be able to share your screen. So Randolph, are you still with us, or are you perhaps having internet problems?
Steve?
Yep.
I'm sorry for having missed the opening. You see, I was working on 6-hour difference, and last week we changed the hour. So it's not any longer 6 hours as it used to be. So yeah, you understand, I was, I thought that our meeting starts at 3 p.m. our time, and it started 2 p.m. our time.
Well, we're glad you're here. Thanks for joining us.
So, all right.
All right. And looks like Randolph had to drop off and is coming back on.
Steve.
Oh, you're back. Good. Okay, great.
Okay. I don't know what's going on, but right now it seems that I can speak and you can hear me, right?
You sound good. So go ahead and share your screen, and on the order of 5 to 10 minute overview of Hong Kong Poly.
Okay, that's good. That's good. So allow me to share my screen right now. Okay, so can you guys all see my screen?
Indeed, we can.
No.
Yes, you're good. Go ahead.
Yeah. Okay, that's good. That's good. Okay, so just let me just put it into presentation mode. Okay, so okay, so hi everybody, and here is Randolph Lam coming from the Hong Kong Polytechnic University. And first of all, I'd like to thank Steve for invitation that allow us to give you guys a kind of an update of a sound and vibration research at at my team. As you can see, we belong to a team called a Consortium for Sound and Vibration Research, and I'm helping as a deputy director, and our director is Professor Li Chen. And just to show you guys a picture, give you an idea where I am right now. And in fact, we are in the nighttime. You will, in fact, right out of my window, you can see all this kind of lighting. Hello? Okay, very beautiful. But as you, okay, so I'll continue. And as you can see that Hong Kong is a very small city, but you can see from the sky view, there are so many buildings, very crowded. That gave us a lot of a noise problem. That's good for us because, okay, we got a lot of work to do to make our city a better place to stay, more acoustically comfort. Okay, And just a brief, okay, of a history of our team consortium for sound and vibration research at Hong Kong Polytechnic University. In fact, we started off as a kind of a research center for noise abatement and control. And then our work got the recognition from the university, and they gave us, a special funding to form a university level excellence research unit in 2007. And we build up that consortium for sound and vibration research. And in fact, this consortium, embrace all the people, faculty members of my university working in sound and vibration. As you can see the whole list here. Well, you can see that a majority of the faculty members come from the mechanical engineering, but we also have other guys coming from building services engineering, or okay, we will have some guys from civil and structural engineers. We hope to provide a one-stop core unit of expertise, okay, to help on the sound vibration problem and pursue the sound vibration research in Hong Kong. In fact, okay, we, just in brief, okay, we will target our activities, okay, in major three directions. Well, as you can see, we want to make use of expertise to provide a better environment for living as far as the noise is concerned. And we also want to provide our expertise to enhance the competitiveness of the industrial products produced by the manufacturers around in Hong Kong and also in the region around Hong Kong. In fact, okay, their bosses are Hong Kong people. And we also want to push through stretch the frontier of the sound vibration technology to develop a lot of enabling technology so that we can have a better progress. And in particular, even though our name called the sound and vibration research, okay, we not only look at the noise and vibration, but we also take a look at the flow together, because they are really tightly connected one another. This is just a brief of a research stream. In fact, okay, that covers all the areas, okay, most a large group of the areas, okay, the sound and vibration. And we give this kind of a very interesting symbol, A, B, C, D, E, F, G, so trying to, to describe the different areas, okay, that's our consortium can really participate, okay. Now, I don't want to give you very details here. In fact, all this information are given in our pre-recorded video already uploaded to the CAV workshop website. And we did a good work. We've been doing good work. We've got lots of good support from different resources from the RGC, like the NSF in US, the ITF, and the industrial projects. Okay, you see that our activity really cover both all the way from the upstream to midstream to the downstream research. As far in the sound and vibration research and the sound and all kinds of sound vibration problems that have a value to our society. And what's next? I just want to give a brief update of the activities that's going on, very actively recently by various staff. Basically, I just want to go through each of these pages briefly. In fact, again, I would invite you to take a look at our pre-recorded video so that you can get more information. We have been, my colleague Li Chen, he's been working on the guided wave structural monitoring, and he also got involved in vibration-based structural monitoring, health monitoring. And recently, he has been devoted a lot to the development of and the utilization of acoustic black hole theory for vibration problem. And again, okay, he also get involved in the topological optimization of metamaterials, which is a kind of a quite hot topic recently. And then, okay, I myself is involved in the flow-induced noise and vibration problem. And well, we are trying to see the possibility of using flow-induced vibration to kill the airfoil noise, or also we try to develop a kind of a direct prediction model so that we get a better understanding how a porous liner works in the flow duct. and some other various design, okay, making use of elastic panel liner. And another colleague he is working on the elastic waiter, which is pretty good for the ultrasonic based damage evaluation. And well, this is well, this all paper I'm not quite familiar, but you know, yeah. And yeah, we also have some new stuff, okay, participating in the nonlinear acoustics, say the parity time symmetric acoustics, which they build up a certain kind of material crystals to show the, you know, exceptional acoustic propagation property, okay, say, or special directivity property. And we don't certain, we also involved in the building acoustic and vibration. Okay, basically it's a reflection, okay, response to the call for the industry. That's okay, they want a better way for predicting the acoustic propagation, noise propagation, and a different way of a noise control for their project, mostly for the large-scale air ventilation network design and the installation project. And well, we also participated in environmental acoustics project. In particular, we are developing the close proximity technology for the, you know, for the special Hong Kong traffic. Okay, as you can see from the figure here, you know, the Hong Kong, there are so many buildings. They create a very, very great street canyon, and that will require us to, you know, to do a little bit more in order to make sure that our tire noise measurement for noise planning, okay, as accurate as we can. Now, and well, in such a short time, I just you know, let you guys through the kind of brief of the update of the activities that we have been working on. And if you are interested in knowing more, okay, we heartily invite you guys to take some time, okay, to our pre-recorded video. Okay, so thank you very much for your attention. Okay, I don't want to take you guys too much time.
Excellent. Thank you very much, Randolph. Yeah, there's obviously a lot going on in Hong Kong Poly. And I'll point out that to all of our guests that if you go to the CAV website and the International Liaisons page, there are links to every one of the groups here. So you can go to their sites personally and check them out further. Plenty of time for questions, discussion.
I have a
question.
Yes,
go ahead.
Hi there. Can you talk a little bit more about your activity related to acoustic isolation of windows? Is this for helicopter application, perhaps, with Lord Corporation?
Okay. Generally, okay, we don't have a helicopter industry here.
Yeah.
But we have so many windows hanging on all the buildings.
Okay.
Okay, and in fact, our work is mainly to develop the kind of the window that provide good noise isolation, yet provide sufficient ventilation.
Oh.
Yeah, because this is the kind of you know, requirement we learned from the government. You know, we really want to make sure that those people living quite close to the roads, those roads are very busy, lots of traffic noise, and we really want to provide a good noise environment not only to rich people. We also want to provide the same kind of you know, benefit to, you know, general people, right? General public. Usually they can't afford you know, keeping the air conditioning on all the time. So the window have to be ventilated, yet provide sufficient noise isolation. We had some success, honestly, and in fact, okay, we have finished the first stage of the project, and we are trying to encourage the local developer to take our approach, so that you know, they can build a very good windows with a good isolation, yet never suffocate the people inside.
So when you say ventilation, the windows provide ventilation. So that means they open the windows, right? Or
This is a special way of a window opening design with the full consideration of acoustic blocking.
Interesting. Okay.
But
Very,
certainly
very
the blocking is not perfect, but
Right.
certainly we have to, make a compromise of these two contradicting requirements. But at
that's
least
very interesting.
from the first stage of our work, it seems that we can do something. And in fact, our idea, we tested out in a real site, several sites, honestly. And it seems that they're performing reasonably good.
Thank you. That's very interesting.
Yes, if you're interested, you write me an email. Okay, we can continue to talk,
Okay.
over the web, whatever way.
Randolph, this is Gary Koopman. Nice presentation, indeed.
Hi, Gary.
Yeah, I have a question for your environmental teams. Are the people in Hong Kong anticipating drone deliveries? And if so, are you beginning to look at drone noise in your center?
Sorry, I can't hear clear. Can you repeat your question again? Sorry.
Sure. Yeah. Are the people in Hong Kong anticipating drone delivery? And if you're going to have drones flying around, are you going to look at this as a project within your group?
You mean drones?
Yes, drones.
The UAV? Is it the
Yes,
UAV?
UAVs.
Yes.
Yeah,
Okay.
UAVs.
Okay.
UAVs.
Okay.
Yep.
Okay. No, he is from another university. I believe you're talking. You mean the Jiangxi, right? Yeah.
Okay.
Yeah. And also another guy. Okay, he is from when. Okay, he has some work on drones, but as far as the works relevant to noise of drones, okay, I know that my good friend Zhang Xin in the HKUST, he has been doing some work on that.
Okay, thank you.
Okay, our environmental noise is much more close to the ground. Sorry about that.
Okay.
Okay.
All right. Thank you very much, Randolph. Let's move on to Yonghua Park from
Okay.
KAIST.
Okay, thank you very much for guys' attention.
Thanks,
I
Randolph.
appreciate.
Yeah, if you'd drop your screen share, and then Yonghua can share his.
Yes. I'm finding the key. Okay.
Yeah, I know it can be tricky.
Okay, and then oh my God.
Yep, here we go.
Okay, good.
All right, so please welcome Yonghua Park from our friends at KAIST. And Yonghua actually has a couple of presentations you may have noticed. One is the overview you'll see now, but he's also part of the AI and machine learning roundtable tomorrow. And in my opinion, that's the better talk. He's got some really neat stuff going on with cough detection and then finger vibration detection. So if you haven't seen that yet, please check it out and sign into the AI and machine learning session tomorrow morning to learn more about that. But today he's going to give more of a general overview of KAIST and some work that his colleagues are doing. So please, Yonghua.
Just a second. Just a second. I have some problem suddenly. I'm sorry about that.
Yeah, we see your screen fine.
But I don't see the main screen. I'm not sure why is that.
Yeah, we see the PowerPoint presentation. It also has the slides on the left-hand side. So it's not in presentation mode, but if you can't figure it out, it's fine. We can still see your slides.
Yeah, so you should see me, and then I tried to share my screen, but I don't know why is that.
Yeah, we can see it.
Oh, sorry about that.
No, that's fine.
Can I switch to my my order of my presentation?
Yeah, sure. We can jump ahead while you figure that out.
Okay.
Goran, are you on? Are you comfortable going next and sharing your screen?
Oh, no, I believe I could do it. Yes.
Okay. So
Just-
Younghwa needs to stop sharing, and then Goran can attempt to share his.
Okay. Do you see
Oh, yeah,
anything?
yeah, yeah.
Yep,
Okay.
you're on.
Mhm.
And I think you just have to click the that mode, and we should be good.
What should I do? Should I disappear or continue?
So you just had your mouse over the presentation. So go down below and click on the presentation button, and it should make it the whole screen. Oop, I think we lost it.
Wait, I'm not sure to have understood correctly. Should I continue or should we resume KAIST presentation? I had some.
Yeah, go ahead, Goran. We'll do you first while Younghwa
All right.
sorts out his computer.
All right. Sorry about it. So I can.
By the way, Goran, I'm back, so I'm ready. So that if you feel you are good to present next to me, then it'll be okay also.
Okay, yeah, Younghwa, let's just go ahead.
Let Steve decide. It's.
Yeah, Younghwa, let's go ahead if you've got it figured out.
All right.
Oh. That was some problem to me. Okay.
Yeah, we do see your screen.
You see my screen, so I'm sorry about that. I'll try again. I found it. I have a dual screen, so that it makes a problem. You
Well,
see my screen, but I didn't see my screen. Okay. So now you can see my screen. Okay.
Yep.
So sorry for the delaying my presentation.
That's okay.
By the way, thank you very much for my the presentation and inviting me to this the CAV workshop. I'm in the NOVIC, Center for Noise and Vibration Control in the Department of Mechanical Engineering at KAIST. By the way, so this year is the 50th anniversary of the KAIST this year. So I'm very proud of this, but I think that this is a very short year compared to the old universities. But I think that the history of the KAIST is the same as history of the Korean industry. So you know that we have a very rapid the growing up in the industry. So in every the industrial sector in Korea, so I think that the KAIST is the same step in every the industrial progress. And my center is also same to this pace with the industry. So let me just shortly introduce the KAIST. The KAIST has the 10,000 students. Okay, so the interesting thing is that the 3,000 is undergraduate, and then 7,000 is graduate students. So this is of the research oriented the university. Okay. So let me introduce the center. We have 6 professors now, and you know that Professor Jung Kwon-ni, he visited the CAV many times. I think that, and he introduced the NOVIC many times. And we have another the young professors. So you can see that the year of the hire up there. So we have the pretty new professors at this moment. This is a big update from our side. So most of them are very interested in the high technology on the electronics, as well as the motor companies, things like that. So I will introduce shortly what we are doing at this moment. So you know that Korea is very strong at the electronics. For example, Samsung Electronics and LG's. They are leading our industries, and also we have the Hyundai and Kia Motors. So these two group, the industries, kind of the leading the energy of our the academy and the industries. So we are pretty keen to these two companies at this moment. So Center for Noise and Vibration Control is our research is very related to, for example, the mobile devices as well as displays, also some the interior car, the noise problems, things like that. And nowadays, AIs and haptics and smart manufacturing are also our research topics. So let's just see step by step. The Jongwon, he is the most senior in our center. So he's now interested in the source identification as well as the rendering of the vibration field in car. For example, he's now trying to control this panel. Okay, so to make a kind of a natural sound in the car interior, including high frequency and the low frequencies. Okay, so Hyundai Motor companies are interested in this one. And also TS has a long history on the intensity-based source localization and some of acoustic metamaterial application for the compact silencers. And Professor Youngjin Park, he devoted the active noise control in a very long time. So his solution is now the working in the Hyundai Motor Company. So and he expanded his idea for some sound design also. So he's now making the good noise. Okay, he's now he's not trying to reduce the sound, but he will generate the good sound in the car interior body. And the more on the active noise control, he is trying to make a fusion between the active noise control and some of the other passive method to maximize the active noise control the performance. And he is now doing some the measurement technique also by using some vision sensor. He's trying to measure the vibration. So you know that the vision sensor is very slow, for example 60 hertz, but he's now trying to overcome this limitation of the frequency up to 60 hertz by using some hyper Nyquist frequency technology. It's very interesting. And Professor Wonju Chun, you know that he is a mathematician, by the way. He is now the making the underlying theories on the acoustic black hole in the point of the mathematics. So the acoustic metamaterial and derivation of its characteristic very precisely in the mathematics. And the acoustic black hole is one of his research, and then it is applied to some the military application like missiles or the cannons. And so the metamaterial in flow, he is now applying the fluid flow surrounding the metamaterial and looking for this kind of the clock. Okay. Acoustic clock in flow. And this is mine. So actually, I was the engineer in the Samsung Electronics. So my research topic is more likely the IT devices. So making the LiDAR system using the vibration of the acoustic the wave, and also the vibration acoustic recognition, which is intensively used artificial intelligence to identify what the sound is, and localization, and also the separation. And some of biodynamic of the recognition for the health sensor application. This is simply the inverse problem of the acoustic wave inside our body. So by identifying the property inside our body, by using the vibration response, we can identify, for example, the glucose non-invasively, for example, or the blood pressure, things like that. And I'm also interested in the structural vibration. Oh, this is one of my recent application of the sound classification. Let's see. This is a cough detection camera which can be used COVID-19 situation. You can see that this is a cough sound, and then you can see where the sound come from. So from this, we can manage this COVID-19 symptom in an acoustic way. So this is now under development for the hospital applications. So you will see more details tomorrow. And Professor Kyung-Gi-wook, he is interested in the soft materials and soft materials control using some of haptics. So he's now using the vibration to give a haptic experience to the users, by the way. So he's now making the flexible sensors and actuators, also the control logic. Lastly, the Professor Yong-Jin Yoon, he is interested in the hearing mechanism, and even he is now want to generate the kind of artificial the hearing the system by using the 4D printing resin. Okay, he's now developing 4D. What is the 4D? 4D means, you know, the 3D printing, and 4D means we have another axis which is time. So as time changes, it changes its shape, and then it can be made from the 3D printer. By using this, he's interested in to make a kind of the vibration and acoustic sensors. Okay, this is a brief introduction of my center. Thank you.
Excellent. Thank you so much, Younghwa. That's a lot of amazing work. We're a little behind, but we have time for maybe a question or two.
This is Julie Simon. Very nice talk. I was curious about your sensors to detect diabetes. What actually are you detecting with those sensors in the reverse problem there?
Actually, we measure the change of natural frequency due to the change of the concentration of glucose inside our body. So if we when we attach some vibration structure onto our body, something like this, and it vibrates, and the tiny change of the concentration of glucose can change the mass property of this small structure, which can be detected by the change of the natural frequency, so that we can measure the glucose in a non-invasive way. So it is a very interesting project.
Wow, that is really cool. I didn't realize you could detect with that sensitivity. What sort of glucose levels are you able to measure changes of?
The problem is not the level of glucose, but so we can measure the kind of a practical the level of the glucose level. For example, the 100 milligram per milliliter, things like that. But the problem is noise. There are many the kind of a complex the structural the uncertainties inside our body, as well as some of the change of change of time will make the change of the result. So that we are now applying, we are now trying to apply the AIs to prevent this kind of uncertainties by using the data-driven modeling, combined with this kind of the physical modeling. This is a challenging research topic.
Awesome. Thank you so much. That is really cool.
Thank you very much.
All right. Excellent. Thank you so much, Younghwa. I think we could discuss a lot of your stuff for quite some time, but we need to move on now to Goran. So if you'd unshare your screen. Yeah, thank you. So if you'd unshare your screen, then Goran, if you could try to share yours again. So a lot of longtime CAV participants are very familiar with Goran and his work. He is one of the greats in vibroacoustics around the world. And he's, again, like Yonghua, has two talks, one where he'll introduce what's going on at INSA, but then he's also part of the AI Machine Learning Roundtable tomorrow, where he's got a talk on smart monitoring of pipe vibrations. But today, it's about INSA, so please, Goran.
Thank you. I'm just discovering that I cannot control my machine, which is a good sign. That means that humans will start to use their brains instead of their computers. The problem is that I cannot put this on the entire screen.
That's okay. We can see it.
All right, but maybe I will do it in a different way. No, doesn't want. Okay, if you're happy with this format, I'm happy to continue. I'll try to be very short, because I'm aware that I'm also responsible for the delay. So we are Laboratory of Vibrations and Acoustics from the National Institute of Applied Science in Lyon, France. This page is a boring one, which shows some statistics. INSA, the mother institution, is an engineering school of medium size. We have 12 departments and 21 research units, which we call laboratories, and something like 660 teaching and research staff. I'm really sorry that I cannot operate this PowerPoint. Don't know how this should be done. So the LVA, which is one of 21 research units, which is Laboratory of Vibration Acoustics, we are 20, out of which 16 researchers, and we have constantly around 30 PhD and postdoc fellows. The financement comes from the Ministry of Higher Education, from collaborative projects and contracts. And our activity is limited, let's say, or focused to four main areas. One is vibroacoustics, which is dealing, as you probably imagine, with modeling and experimental work on noise and vibrations and their interaction, both of mechanical and fluid origin. Then we have another activity which is not completely independent, of course, but which can stand for itself in view of the aims, which is the identification, where the usual task is to find in a backward way either the acoustical or mechanical properties of sources, components, and material. Then there is an activity which is apart, which is subjective perception, which is a field very much in demand and constantly developing, and which is about having the relationship between the stimuli of vibration and noise and the discomfort these phenomena create to humans. And then the fourth area is monitoring, diagnostics, and non-destructive testing, where we have condition monitoring of machinery, especially rotating machinery, identification of or localization of defects by acoustic and classical acoustic vibration techniques, and use of guided ultrasound waves for the same purpose. We have a few facilities. to carry out experimental work, a large reverberation chamber, a large semi-anechoic chamber, and a few other chambers which are dedicated to specific type of research, as you can see from these titles here, I believe. Now, we have made a video presentation as it was required by the organizer, and you have details there. And if you ever dare to look at this video presentation, you will see that instead of listing a lot of different projects which we carry on, we have selected as a representative 3 of these projects. I will very shortly go through them. One is about creating artificially turbulent boundary layer excitation for experimental work. We know that turbulent boundary layer excitation is a major source of noise in many circumstances, aircraft, other types of vehicles, ships, etc. And the way this is done is that the turbulent boundary pressure is synthesized from turbulent boundary models, which is not such a simple thing because the models is of statistical nature, and then using the turbulent boundary pressure realized in many different realizations because it's not uniquely defined. We can go upstream and look at how to create such a pressure by using not the natural type of excitation, which is flow with turbulence, but rather a stationary and well-controlled excitation such as a loudspeaker. And after several years of development, we seem now to have a technique which does the work well. On the bottom of this slide, on the right, you see a comparison between a measurement shown on the left done at the University of Sherbrooke, and which is one of international liaisons to CAV, and the synthesis of vibration of a panel used in the experiment, done completely independently in France by the technique I have outlined here. So we think that with such a quality of reproduction, one can have a fairly reliable way of having an artificial turbulent boundary layer excitation. And then I go to the next slide. It is about modeling of anisotropic multi-layer panels. The problem here is that the multi-layer panels, which can have layers of very fine structure, are difficult to measure by numerical techniques, and analytical modeling can be advantageous especially in use with codes like finite element codes. So the idea here is to find an equivalent panel out of multi-layer and orthotropic layers which may not be orientated in the same direction. The method to use is so-called zigzag method, which was developed in our laboratory some decades ago. But the original method was developed for homogeneous and isotropic layers, while the new method is extended to orthotropic layers of different orientation, which makes the panel completely anisotropic. And the technique is, those who wish to know a bit more about the technique, they can use the video to go in it. Here is just an example of one of results of obtaining equivalent properties, which for an anisotropic equivalent plate consists in finding 5 different elasticity constants, which unfortunately are not constants, but which change with frequency. So 5 elasticity parameters function of frequency. And the third example, which illustrates our typical activity, is the one of airborne source characterization using a particular technique where the field due to a source operating is reconstructed using a concept of so-called virtual acoustic volume. Again, I call those who might be interested in the technique to refer to the video. Here we see the engine on the left, which is a source of noise, with the functional parts colored in different colors. And on the right, we have a chart showing the contribution in third octave bands to radiated sound power from different of these components. So one of possible outcomes of this type of source characterization is that we can assign to each component a percentage of acoustical power which is radiated, because the method allows to reconstruct fully the acoustic field on the surface of the source. Just want to mention that the measurements are not done on this surface, the measurements are done elsewhere, and the procedure is a bit complicated to explain in a few minutes, so I leave this to the video. And I believe this ends my presentation. Hope that most of the listeners are still alive after it. And I'd be glad to answer questions, providing that I know the answer.
All right, thanks very much, Goran. I think we have time for one question.
Hey, Goran, this is Gary Koopman. Good to see you. Good to hear you. Hey, on your last example, the engine was driven by I think you had a force transducer. Is there going to be a relationship between what you found for your source characterization when the engine is actually running under, firing as a normal engine? Would there be a good correlation there?
Well, I think this result, I believe a colleague who is much more involved in this particular research than myself is listening to our talk, so I mustn't say just anything. I believe that these particular results, a result which shows the how the radiated sound power is spread across the surface of the source, is obtained by an artificial excitation by a shaker-driven engine instead of the natural process in the engine, which would normally be required, of course. But the technique was conceived to operate into real life conditions. That means that all the perturbation, which such as reflection from the surroundings, which is not anechoic, then noise from sources other than the source we investigate, and perturbations out of supporting structure of the source, all this is taken into account by this concept of virtual acoustic volume, where the volume is acoustically modeled, and also within this volume there are transducers which measure the sound pressure, for example, and all of this taken together can give us the reconstruction of both the pressure and particle velocity on any surface within this volume, comprising, of course, the surface of the source. So I don't know whether I came anywhere near the response to your question.
Thanks, Goran. That's a good one. Thanks.
Right.
All right. Thank you again very much, Goran. We do need to actually finish at about 5 minutes till the top of the hour so that we have time to start the virtual lab tour afterwards. So we've got 4 to go, and that gives us about 50 minutes. So you guys do the math, you're engineers, so maybe the talks have to go down a little bit in time so we have more time for discussion. But next up is our old friend, Robert Meyer from DLR, filling in for Lars Enghard. And Robert is, again, an old friend of the CAV. If you want to go ahead and start sharing your screen, Robert took his family to Penn State a few years ago for a sabbatical and spent some time doing some nice flow measurements in the aerospace department. And we're pleased to have him with us again here today. Robert, are you able to share your screen?
Yes, thank you, Steve.
Excellent.
Thank
yes,
you.
Please go ahead.
So, hello to everybody. I'm really happy to that we got the invitation and give us the opportunity to present our department. Unfortunately, Lars Enghard, who headed our department, is not able to give this presentation, but he has recorded it already, so details can be seen on the recorded version. So that's why I tried to hurry up a little bit so that we are on time. So a few words to the German Aerospace Center in Germany. It's a national research institute, also working on space agency and project management. The research areas are aeronautics, space research, transportation, energy and safety, security, and digitalization. So here you have a map of Germany, and altogether we are 9,300 employees working in 51 research institutes. Our mother institute is the Institute of Propulsion Technology, and which is located in Cologne, and our Department of Engine Acoustics is located in Berlin. We have also, or DLR has also offices in Brussels, Paris, Tokyo, and Washington, DC. So here you see the topics of our department, the core competencies. So we are dealing with the turbo machinery sound sources, the engine core sound sources, also the sound sources of jet noise, the unsteady aerodynamics and turbo machinery, which is my personal subject, where I'm working in. And other topics are the sound propagations and ducts, sound radiation, and the sound source localization with microphone arrays. We are working also on sound absorption by liners, on active flow and noise control, where I'm also working in, and we have a huge aeroacoustic prediction, pre-design department and experimental facilities, as well as methods and tools. So I want to pick out 4 examples which has been happens in the last year. So we are just in the next weeks we will get a new test facility which is called CRAFT, Counter Rotating Acoustic Fan Test Rig. And the concept of the setup is that we have it's a very cheap test facilities which can be driven in our department. And it's very flexible and with low operation costs. And the experimental investigations are mainly on aerodynamics and acoustics. We have plenty of parameters which can be changed. We can drive this test setup with a rotor, a stator configuration, as well as a rotor configuration. There is a very long cantilever hub, about 1.5 rotor diameters, without any disturbances here. And also the axial distance can be changed of the system. Also, we can, you see here some physical data. So the maximum RPM is 4,500. The relative tip Mach number is 0.33. And the rotor diameter is 452 millimeters. So you see here the full setup. So we have an inlet control device. The flow goes from left to right. Then we have an inlet, the arrangement here of the rotor counter-rotating arrangement. The two engine motors, electrical motors, are located outside. And we have plenty of possibilities with microphone arrays, line arrays, and circumferential microphone arrays. And in the end, there is an aeroacoustic throttle with low aeroacoustic reflection. And you see some photographs here from that. So we plan to have the first run in 2 weeks. So we are very, very excited. Yeah. So the research topic on that is the influence of inlet distortions on fan noise. And also we want to investigate 3D shape optimization for low noise designs, with a focus on tonal noise as well as on broadband noise. And the advantage is that we use a rapid experimental validation of numerical tools here. So that brings me to a second part, the design to noise for especially on fan noise. So we have plenty of different tools available. We for the design of aircraft fans, and the easiest way is the 1D mainline, where the very few input values are only needed, and this can be used for trend studies possibly. Then we have a 2D through flow design, which will be coupled in future with our with a pre-design of the whole engine. The GT Lab is from our mother institute in Cologne. And the 3D runs solution here, where the input data taken from stationary flow simulations, this gives the possibility with realistic geometry and flow boundary conditions, and it's low cost in comparison to the unsteady scaling resolving simulation. And the most, the other one is the 4D harmonic balance unstationary solver with a U-runs approach of our in-house code trace. And this is coupled with our noise prediction tool for the broadband and tonal noise. So some examples what can be done with these tools can be seen here. So this is shows an optimization of an outlight guide vane stage. So there's a rotor blade and the outlight guide vane, and we have a target function with 3 different point optimizations. So the focus was here on the cutback bypass overall sound pressure level, as well as the approach bypass overall sound pressure level and the cutback efficiency here. And our optimization tools creates several, I don't know the exact number, but probably up to 100 different samples. There's an automized geometry generator, and afterwards it's calculated by the RANS approach and the noise prediction tool. So this shows the result here of the member M517, which is this one here. And you see a difference in the tonal noise of cutback by minus 3.8 decibel. And in the approach case by minus 8.5 decibel. But on the other side, the broadband noise for cutback is increased by 2.1 decibels and the approach for 1.7 decibel. The efficiency is slightly changed by 1%, minus 1%, but you can see here that there are plenty of different solutions found, and it's very interesting to see how the geometry is created by this optimization. So here you see more conventional design, where the tonal noise reduction is a little bit less than in the other case, but it seems to be more realistic to build this. And still we have a noise reduction in the tonal noise of 1.5 and 4 decibels. And the broadband noise increase is only slightly, but there is no efficiency deficit can be seen here. So
Say, Robert, I apologize, but we need to make sure we get everybody a chance. Is it possible to maybe just show very quickly the last 2 slides and people have a chance to maybe ask you a question? Because we've got to
yes,
be finished by the top of the hour. I'm sorry.
yes. So there are 2 more topics. So one is the pressure control wave for a combustor test rig. So this is very, very loud in our test facility for pressure for the operating. This controls the operating pressure of combustors. So we built up in a scaled model a noise reduction technology, which can be seen here. And the results are up to 20 to 30 dBs in our test facility. Details can be seen in the presentation. And the last one is we are working, we just started with that, the influence of propeller blade counts on drones of quadcopters for the perceived level of noise annuations. So we like to change the number of blades and speed variation and the blade shape, and to receive the relative frequency shift and the beat noise. Okay, so very quickly.
Yeah, thank you so much. Apologies for that. We just have to make sure we start the next one on time. And we have time for one question, which I know won't do the presentation justice, but.
Hey, Robert, this is Jose. Great hearing from you.
Yes, hello.
Yes. Is your shape optimization applicable to rotor blades designs, thinking about UAVs and potentially coaxial configurations?
In principle, yes. So we of course we are part of the Propulsion Technology Institute, so we are mainly focused on aero engines, but I don't see any reasons why that shouldn't be used for other applications as well. And you see the drone project here goes as well in the same direction. Of course, we want to use this technology also for the design of the blades here.
Excellent. I'm gonna go ahead and hunt for some of your papers then. Very good. Thank you.
Yeah, please contact Lars Enghardt for that.
All right.
Excellent. Thank you very much again, Robert. And We've got 3 to go and about 40 minutes, so to leave time for some discussion. We're getting a lot of good discussion today. Please, Filippo, Klaus, and Olivier, try to keep the talks to a little bit under 10. So next up, we have Filippo Fazzi from ISVR, one of the first CAV international liaisons that I believe Gary Koopman recruited many years ago. Ah, very nice, Filippo. I think they're a little bit older now than when I saw them the other day.
Looks like a noise control application right there.
Okay, we can see the screen just fine. But we can't hear you, I'm afraid.
Sorry, I was
there we
talking
go.
all this time. Thinking you could hear me. Hello,
We've all
everyone.
done it. It's fine. Thanks. Go ahead, please.
Can you hear me okay now?
Yep, you're good.
Excellent, thank you. So my name is Filippo Fazzi, and I'm a professor and also director of research at the Institute of Sound and Vibration Research. I'm going to give a very brief highlight of some of our research at the Institute, and also focus a little bit on my research, but of course, all the detail of that is in the recorded presentation I gave. So for those of you who do not know us, we are here in the sunny south of England. In fact, I think, Stephen, we had, thank you for kind of promoting it to Australia, but the British weather reminds us all the time that we are in England here, lovely country in any case. And yeah, so at the ISVR, Institute of Sound and Vibration Research, we are about almost 60 years old as an institute, and we're roughly 35 full-time academics and a bit more than 100 PhD students and researchers overall. And our research activity spans a very broad spectrum in the field of acoustics and vibration, including aircraft noise and air acoustics, signal processing and active control, audio engineering, which is my field really, underwater and ultrasonics, vibration and acoustic related to vibration, including also the effect of sound and vibration on humans, and last but not least, the hearing and balance center, so audiology. And you might be interested to know that now we can regrouped into 3 groups. One of these groups is the dynamics groups, and they do fundamentally, as I said, dynamics and vibration, but also study the effect on vibration on humans. You can see here a subject on one of our shakers. I call them the torture chamber because I shake people for as long as I can take. And when they say it's enough, they say, okay, this is the standard. Anyway, this is one of the fields. In terms of acoustics is probably our largest research economy. Not probably, definitely our largest research economy. We are very proud to host the Rolls-Royce University Technology Center, with which we carry out much research in this field for a very long time. You can see here just few examples of the research that we do. That includes both, a computational model and experimental activity here on liners, the trailing edge and leading edge optimization, as well as noise control with acoustic liners and contra-rotating propellers. Again, more detail on that, just very brief outlook. Don't ask me too many difficult questions on this because it's definitely not my field. Anyway, the acoustic group is very active, and just recently we've been awarded a very large project called Fantasia in collaboration with Rolls-Royce. More detail to come on that. Another group, which is the third and youngest but also largest group, is the signal processing, audio and hearing group. I will not be able to cover all the activity that we do here, but just to highlight what is our second largest research economy on control, really. We are very proud to host the BAE System for Center for Research in Active Control. So it's called CRAC, Center for Research and Active Control, and is mainly focusing on active control of vibration for maritime applications, so preventing ships and other vessels to generate sound. Also, this is strictly on the right-hand side of the slide. This is not strictly speaking ISVR, is one of our enterprise units, but is a spin-off of our institute, is the Auditory Implant Center, University of Southampton Auditory Implants Service, sorry. And they're very successful in doing research and testing and installation of cochlear implants for people with a profound hearing impairment. what I thought it would be quite interesting for you to know about is some of our research in active control with head tracking. So as I'm sure you all know, when in active control, it's much easier to control lower frequency than high frequency because of the wavelength problem. But one of the applications that my colleagues Steve Elliott and Jordan Chia developed with their students is the use of a camera to track the listener, as you can see in this video here. And because of the camera, the active control is kind of localized in the proximity of the ears of the listener, so achieving a much higher effectiveness at high frequencies. And this work was carried out in collaboration with Jaguar and Land Rover, another long-term partner, industrial partner with our institute. There you go. And now I would like to focus a little bit briefly on the research that I carry out with my team, the Virtual Acoustic and Audio Engineering team led by myself and Professor Philip Nelson. It is all about 3D sound, sound field control, but especially the use of loudspeaker arrays. Here you can see loudspeaker arrays of all different shapes and size, which is one of the largest one, 40-channel loudspeaker array. What I think is interesting is to perhaps talk to you very briefly about the theory, because this is very much related, the way we do kind of sound field control for audio reproduction, to the theory of acoustical holography. So very briefly, from a mathematical standpoint, let's assume we have on this red sphere distribution of loudspeakers, and then we want to control the sound field, as in reproduce a target sound field on the surface of this smaller blue sphere that ensures also an accurate reconstruction in the interior. And the way we do it, we formulate a so-called forward problem that relates this function Qy, which is the source distribution of this external sphere, to the pressure on the smaller blue sphere. In this case, is with an integral equation, because we are assuming a continuous distribution, but it can also be discretized. And in order to define, once we have a target sound field P, we need to define what is the required loudspeaker strength, loudspeaker signals to reproduce it. So we need to invert, in this case, this integral operation. And this is indeed very, very similar, if not identical in many ways, to acoustical holography. And in fact, what we do shares a lot of similarities with acoustical holography, with the difference that for acoustical holography, a solution always exists for the problem. It might be sometimes hard to find the solution, hard to calculate, but it always exists because it's generated by a physical problem. Whereas for sound field reconstruction, that might not always be possible, especially if you ask something unreasonable in terms of our target sound field PX. Another area of interest now is related to more to kind of virtual acoustics, and is about the delivery of sound, accurate sound, to the left and right ear of a signal using a loudspeaker array. This is called crosstalk cancellation. And if you like, a simple way of explaining it is like creating virtual headphones. Indeed, if you are capable of reproducing exactly the desired signal at the left ear and right ear of a listener, then we can create ideally any acoustical illusion. It is in fact virtual acoustic, as it were. And as you can see in this example, you see here on the top a model of a loudspeaker array. And as you can see here, the loudspeaker array is focusing a very sharp beam of sound on the left here, as you can see, and try to minimize the acoustic energy in the right here. And by doing so, we can independently address the signal at the two ears and create, as I said, an arbitrary, a very, very, very good and very convincing acoustic illusion, including sound coming from behind you or far to your right, even though the loudspeaker array is from the front. The main limitation here is that as soon as the listener moves from the so-called sweet spot, the sound beams are not accurate, they're no longer focusing on the ears of the listener, and the acoustic illusion falls apart. This is why, also in this case, we are using a camera. So as you can see here, this is one of the prototypes generated by one of our startup company, Audiosonic. We are included a small camera in a loudspeaker array. So when the listener moves, we can track the listener. And as you can see in this animation, where you can see here on the top, a loudspeaker array, and here the two ears of a moving listener. In blue and red, you can see the beam patterns of the beam for the left and the right here. And as you can see, when the listener moves, because the camera can track them, then also the beams, the two acoustic beams that delivered independent sound, follow the listener, thus providing consistently an accurate 3D image. And that was a bit of a rush, I apologize, but I hope I kept, I was good in terms of timekeeping. All the relevant detail of this presentation are, of course, in the recorded presentation. Thank you. Happy
Excellent.
to answer questions.
Thank you, Filippo. We have time for a question. So one question I always have with these really cool systems, with all these sensors and speakers and all of that, is what if one of them goes out? How robust is the system if one or two speakers either just starts dying or the phase starts drifting on you? How well does it perform then?
Well, thank you for the question. It's a very relevant question. It's always kind of a trade-off between the performance and the ideal performance and the robustness. So you can compromise on one, and is to be honest, is exactly the same as an acoustic holography, in fact. So you can have a very accurate answer, if you like, to your measurement, but very unstable depending on your condition. As soon as you have a departure from this ideal condition, things get worse very quickly. Or you can have a less precise but more robust answer. Same thing with the loudspeaker array. So you can really push the performance. And when you push the performance, especially think about this case when you're trying to create very directive sound beams, even a low frequency. So you need to use a lot of destructive interference, relying possibly also on evanescent waves and so on. So you can push the performance of the system quite hard, but you must prepare that as soon as one of the loudspeakers starts distorting or they go out of phase because of time drift maybe, then the performance fall apart. So also in this case, things like the accurate tuning of a regularization parameter or so on are really crucial. And getting the right trade-off between performance and robustness is an engineering challenge very often.
Sure. Excellent. Thank you again, Filippo. And again, apologies to everybody for short times, but these are the times we live in with Zoom meetings, I'm afraid. So thanks again. So next up, if Filippo, you'd drop your screen share, we have Klaus Claes from KU Leuven in Belgium. And believe that KU Leuven just came through their own large meeting, all done virtually, of course. And I'm curious how that went, Klaus, if you participated in that or not, by the Dynamics consortium you guys do. Yeah, Klaus has been at CAV before, I think a couple of years ago, and we're happy to have him again now.
Hello, can you hear me?
You just need to switch your settings over to...
Yeah, I was afraid. 1 second. I will try to share my other screen.
Yeah, there's an easy way to switch it if you can't.
Okay, wait, let me just try to... So yeah, now it should be working properly. And I'll just start the presentation. My apologies. Now it's fine.
Yep, perfect. Yep.
Yeah. So I intend to stay well below my 15 minutes. So no worries there. Okay. So thank you for having us again, Steve. So we're the University of Leuven. Maybe as a quick introduction, remind everyone where Leuven is. Leuven is located in Belgium, quite close to other capitals as Berlin, London, Amsterdam. We're also close to Brussels, only 30 kilometers away. And for the people that haven't been in Leuven yet, it's a very nice, small city, around 100,000 inhabitants, and it's a nice atmosphere. So everyone who would like to visit us in a post-Corona time, please do. I think you will enjoy your time. Our group itself, we are a group, I think we originated in the 60s, and we are now a bit over 90 persons. I think in total we are over 100 persons actually. We are a bit over 90 PhD students. We have 8.5 academic staff in our group. And one of the nice things in our group is that you have quite a bit of industrial PhD. So quite a bit of our PhD researchers are actively involved in collaboration with industry. In our group, we focus on vibroacoustics, air acoustics, multi-body dynamics, smart system dynamics, and structural reliability and uncertainty. And that's also, as you will see later, one of the things that we're now trying to do is to get more and more interaction between the different domains ongoing, to try to leverage a bit more on the size of our group. And if you look at our group, the thing that unifies us across the different branches is that we have this common strategy of creating added value during every phase in the lifetime of mechatronic systems, so being design, manufacturing, or operations. And the unifying principle is that we want to understand and control the dynamic behavior of those mechatronic systems. And the concepts that we believe strongly in are the model-based system engineering and digital twin concepts. So in everything that we do, we try to combine preferably physical behavioral models with measurement data and try to get additional insight in the system to better understand that system and to come up with better solutions or better control systems. So that can be from a condition monitoring point of view, or that can be from a lightweight structure design point of view, or everything in between. That's also something which is represented in the development and validation platforms that we invest in. So we have quite a wide range of different experimental setups, going from shaker tables, so this is a 6DOF Clear Freedom hydraulic shaker table, up to acoustic characterization equipment. In everything that we do, we try to have validated models, or at least good estimates of the input forces, such that we can truly update our models and go that next step in combining models with experimental data. So that also means that we invest heavily in modeling software to get the most out of our experiments. If you look at, or if you listen to the presentation that we recorded, there we focused on two main activities, and I will briefly highlight them. So one had to do with model acceleration techniques, and that is a bit linked to what I said earlier, that we're trying to get the most out of the combination of the different activities in our group. So here's an example of gear MVH. And as you see, to our activities there, we start from the source of quite elaborate gear models or bearing models that can go from full finite elements up to more lumped 1D parameters. And those models we can combine with our flexible multi-body toolbox. And then that one we're now trying to couple with our acoustic and our vibroacoustic models. So going from finite element to boundary element methods in such a way that we can actually go to a full characterization of, for example, gear whine, that we can see at the most detailed level what's going on, what is the cause of this noise, and how that actually influences how that noise is being perceived by the receiver, such that we can model everything from source up to the pressure at the ear location of the passenger in a vehicle. And then besides doing everything in models, we're heavily investing in also being able to check the different level of our models with testing. So that can go from gearbox housing, component testing to see where our structural model is on point. We're also building this kind of, in this case, gearbox setups where we can actually characterize those gearboxes and see where our source models are correctly, the transmissions errors that we're predicting, whether we actually see that also popping up in reality. And then, of course, the goal is to do full system testing too, so to actually put that gearbox in a vehicle and test the levels at passengers' ears and see whether we capture the trends that we predicted in our models, and then use that data to do model updating and to close the full loop as you wish. And there, in order to enable that, one of the things that we have to invest heavily on is model acceleration techniques. And so in the talk that we recorded, there we go a bit deeper in the different strategies that we follow with finite element and boundary element methods to get those acoustical models and vibroacoustic models better up to speed. And then next to this entire closing the loop between models and experiments, we're also still investing in MVH control itself, in new materials or new material structures to get better vibroacoustic behavior. In the past editions, we almost always had a small section on our metamaterial work that was always focused on the vibroacoustic metamaterials, where we use this kind of structural stop-band behavior to achieve zones of strong vibration attenuation or acoustic attenuation. Now, recently, we also moved more towards the area of acoustic metamaterials. And one of the recent works there is to work on this kind of phase gradient-based materials, in which if you use the generalized Snell's law, it's known that if you have a certain phase gradient over a material, it should be theoretically possible to have no reflection and to have no transmission throughout your material with a phase gradient. And by using some kind of discretized approach of that phase gradient, we can achieve this kind of foams or foam assemblies, which have these broadband absorption characteristics, both broadband in frequency, as working over a broad range of angle of incidence. So that's one of the new things that we're working on. And in the presentation itself, we also go a bit deeper on how we do the characterization of these materials and how that we built this setup, which also was a bit less trivial than you would first think. So that was in a very short nutshell the activities that we highlighted in our talk and what we're about. If you would like to have some more information, yeah, please visit our website. We also recently made an overview movie that visualizes a bit the activities that we do, which is also nice to see. So that was a short update from my side, Steve.
Thank you very much, Klaus. Yeah, perfect. And again, there's a lot more detail in the pre-recorded talk. So do we have time for some discussion? So you didn't bring it up in this quick overview, Klaus, but I did notice in the pre-recorded talk that you guys are using a boundary element. I don't know if it's necessarily modal acceleration or something else. I think it had the initials MOR, but it was a way to accelerate the boundary element performance. I don't know if you could briefly talk about that. And I know there's a lot of, again, last 10 or 15 years, advances in boundary element methods to use things like H matrices and adaptive cross approximation methods. I just wonder what the difference is between what you guys are doing and those other methods.
Yeah, so I saw your question popping up on the YouTube channel, so I came prepared. I asked the researcher what I should answer to your question, because it's not my topic. I'm more towards the material side of things. But he indicated that basically the main difference is that the methods that we are investigating work across frequency. So the assembly of your matrices, you do it once to then use for multiple frequencies, while the methods that you refer to, Steve, are more need to be reused for every frequency separately.
Right.
So our methods should work a lot faster if you do simulations across a wide range of frequencies. That would be the main advantage.
Okay, and even though it's not your topic, do you have, can you briefly describe the basic idea behind the MOR?
I should be able to, but I lost my, I'm quickly thinking on the difference again between the finite element and then the model order reduction strategies that we used in the binary element methods. But I'm sorry to say that I cannot quickly recapitulate.
Oh, that's okay.
My apologies. But
Yeah,
I did
maybe.
my best in the video, so yeah, the interested participants can check it there.
Yeah, sure. If maybe there's a paper that your colleagues have written on it, that might be
yeah,
good
and
to
that's
pass
for
on.
sure. We have a lot of papers on that, so if someone is interested, please reach out and I will bring you in touch with the right persons.
All right. Well, thank you very much again. And we're down to Olivier. And it's always tough to go last, but thanks for your patience, Olivier.
No problem.
So,
Can you hear me well?
we can hear you well. And I believe your colleague Alain Berry is also on the line from Sherbrooke. And we're always pleased to find out what's happening north of our border. Less COVID cases for sure. And a lot of exciting research at Gauss. So please, Olivier.
So can everybody see my screen?
We can.
Okay, so I'll try to be brief. So thank you, everyone. I'll try to give you in 10 minutes a quick overview of the lab and a quick overview of deflectometry and what we are currently doing at Sherbrooke concerning this. So my name is Olivier Robin and I'm working as a research professional at GAUSS. So the GAUSS laboratory, can you see my mouse pointer?
Yes, Olivier, yes.
Yes, thank you.
Yes,
so
yes,
when
yes.
you're at Montreal, it's 150 kilometers east from Montreal. It's at Sherbrooke. And I'll be brief on this, but the GAUSS is the largest Canadian research center in terms of acoustics. Overall, 4 global research areas: materials, test and characterization, vibro and aeroacoustics, active controls, structural health monitoring, and sound field reproduction. What is wonderful at the GAUSS is that we really have large infrastructures and equipment, including a 96-channel WFS, a 50-channel ambisonics sphere, a reproduction sphere, a wind tunnel in anechoic room, a 3D laser vibrometer, and we also have the chance to have a coupled reverberant anechoic rooms up to 250 microphones and also high-speed cameras. So this is a wonderful environment to work in. In terms of collaborations, I would like to underline that apart from being a CAV, International Liaison, and again, thank you, Steve, for that, and the CAV, an international research project has been launched in 2019, which is the Centre Acoustics Jacques Cartier. So it's a France-Canada network between Le Mans, Lyon, and Sherbrooke to develop research in acoustics and vibration. So that's pretty new, and it involves a lot of people. So we are pretty confident that this will give a new impulse to the research between France and Canada. We also have growing collaboration with the CERMIT, which stands for Center for Interdisciplinary Research in Music, Media, and Technology, which is based at Montreal in Quebec. So here are a few examples. So we are making research in sound field reproduction, 3D audio. This is mainly things in which Alain is involved in too. So this is a picture of the anechoic validation of a hybrid method, which combine a sphere of 50 sources with a circular array of 32 sources. In this field, we also now digging into interdisciplinary research in the broad area of music and sound, including sound perception. So this is pretty new. We are making spatial audio recording of skilled musicians in various conditions using a binaural head, typically a mannequin. And we also trying to explain better to people what sound is. And so we are 3D printing the sound directivity of instrument like the trombone here on the left. And this is really new at GOES. And we are trying in this, following this dissemination direction, trying to do more and more on this field. So we're setting up, so this is a work in progress, but will be shared with the CAV, but we are doing binaural recordings, again, of skilled musicians for several reasons, to make musicians aware of what is binaural or spatial recording, but also to be able to explain to people what does it involve and what does it bring, into the sound perception and possibilities. Another area is, let me see. So it is also the use of comics to explain research. So this is being held by myself. And we're trying to use comics to convey information to people in general. So this is about noise, and to explain why we are trying to reduce noise and improve comfort. Another possibility is that one, which is in French, which explains what is higher acoustic simulation with intriguing and pretty wonderful onomatopoeias to explain people what we're doing again as acousticians. So now briefly, last one is we try to include research in a variety of media, including museums. And this is an example of sound, OmniSound, which was developed with Sherbrooke Science and Nature Museum. We had the pleasure to be awarded the 2020 Best Exhibit Award for this. So this is meant for explaining to young people, especially, what is sound, why should they be careful to their ears. And we were also able to include research in the form of listening, an audio polling station to crowdsource our listening tests. So now I'd like to make a really brief introduction. I think I have 5 minutes left. Steve, can you confirm?
Yeah, but if you want to leave a minute for questions, maybe 4 minutes. Otherwise, we got.
Okay, let's go for 4 minutes. So that's okay. Going to be quick but interesting. I hope so. So the deflectometry principle, which is a full field vibration measurement technique that has been explained at CAV last year, is pretty simple. If a grid is reflected on a reflective surface, and if you acquire an image of the 2D grid without and with loading, the difference of phase map between these two images will give you directly the slope maps on the image surface, because we can have simple geometrical relations between slope fields and spatial phase maps. So in the lab, it takes this form. This is a high-speed camera on the left, a lighting on the right. You got a reflective panel, which was simply polished using car body polishing techniques, a printed grid, and then you got a recorded image on the high-speed camera. I'll skip the details, but when you compare a measurement on a panel between a laser vibrometry measurement and the deflectometry measurement, generally speaking, the deflectometry outperforms. Deflectometry in terms of number of points, in terms of spatial resolution, and in terms of acquisition time. But the problem is that you need a mirror-like surface to apply deflectometry. So you can use reflective mylar. This was studied by Gary Rhodes, a master's thesis at CAV graduate program. But another solution is to move to infrared deflectometry because of the radius criterion, which relates to wavelength of light and the surface roughness. So it gives you an indication of what the surface roughness should be compared with the wavelength sunlight, so that you get a specularly reflective surface. And in the visible spectrum, the wavelength is approximately 500 nanometers. So you need a small roughness of 60 nanometers to have specular reflection. In the long infrared spectrum, you're getting to a wavelength of 10 micrometers, and the roughness, the softness roughness is largely relaxed. So we decided to test it on a simple test case, and we compared visible and infrared deflectometry at GOES last summer. So the test case is simple. You got a simple cantilever beam under impact, which is impact right there. One side has a mirror-like finish, and the other side is left unprepared. And we simply set up the method for these two cases. So the first case is using a high-speed camera, a printed grid, and a measurement on the mirror-like side of the beam. We were able to make high-speed and largely refined spatial measurements. Then we tested the same using an infrared high-speed camera, a thermal grid, and a measurement on the unprepared side of the beam. So what is a thermal grid? Briefly, this is a grid that has a contrasted emissivity between two elements that compose. So in the case, it's a PLA and an aluminum. And just a quick comparison of the results, which is really interesting, is that if you compare the theoretical vibration, the displacement map, so it's mode 1, mode 2, mode 3, mode 4, and mode 5 of the cantilever beam, and if you compare it with visible deflectometry and infrared deflectometry, you see that we are able to obtain finely resolved in terms of spatial resolution measurements. And with infrared deflectometry, even if the sensors are pretty bigger and the largest frame rate is smaller, we are really able to obtain comparable results. So just to summarize, we made the first indeed comparison between visible and infrared deflectometry. And this comparison showed that it is possible to use infrared deflectometry on common materials. And what is really intriguing and interesting for the future is that all the established methods and algorithms for image processing are just identical, so that it makes it easy to move from one to another. And so the range of materials and surfaces that now can be tested using the deflectometry is clearly broadened. I'll stop here, maybe to.
Excellent. Thank you again, Olivier. And those of you that have been, I think it was the last year's workshop, Olivier came in and did a demo of this really neat method with Micah Shepard, showing a lot of promise for sure. That infrared seems new to me. I think we have time for a question or two before we jump off to the next session at 11.
This is Yongwa Park from KAIST. So I was simple questions. In the deflectometry, you apply it to the flat surface. Can you apply this technology to the general shape of surfaces?
Thank you for this question. Yeah, for the moment, deflectometry is restricted to plane surfaces. The theory is being extended to curved surfaces, but this, I would say that this is currently restricted to plane surfaces. Nevertheless, we're confident that this should solve a lot of problems because many of the structures that we are studying or dealing with, especially in the lab, are usually plane structures.
Okay, thank you. Very interesting.
All right, anything else? Just Olivia, real quick, I think I put this on the YouTube, but have you thought about using two cameras? I know we do that a lot for flow measurements, so we'll have up to maybe even 3 or 4 to get stereo imaging.
Yeah, this looks like photogrammetry indeed. When you're speaking of this, this might be an avenue, Steve, but to be fully honest, we never thought of trying to apply the deflectometry using such stereo setup. But that might be a possibility. Indeed, this is what is being done when you're making 3D DIC. You're using 2 cameras and a speckle on the surface to be imaged. So that might be a possibility. But it has never been tested here at GOES, but never in the world, I would say.
Yeah, we have attempted the speckle stuff with just commercial off-the-shelf tools from Liaison, for example. And it works fine if there's really high vibration, not so much if it's small. The digital noise floor is quite high, unfortunately. And that's the nice thing about your method is you find a way to amplify that significantly. So you've got a good signal to noise floor.
Yeah, what I can say is that, especially at GOES, we are beginning to think that maybe a solution is to make hybrid solutions. Like maybe using, some people try to use a deflectometry setup and mixing it with the DIC post-processing. So I think maybe the future for these methods, optical methods, is to try to make hybrids, using the post-processing of one technique, using the setup of another one, and so on.
Yep, I agree. Excellent. Okay, so I think perfect. We're have a few minutes before the next session. Thank you very much to all of our international liaisons. I'm grateful and just humbled by your devotion to the CAV and participating this year in spite of how difficult it is. Thank you so much. The next session is starting in 3 minutes. So and we're going to wait a little bit because we realize this ran a little bit long. But that's Michelle Vigilante talking about her oralization and sound reproduction lab. We've seen a couple of our speakers talk about that today. Olivier and Filippo, for example, have sort of similar setups in their own institutions. But what Michelle's doing is really neat. They're doing acoustic mold analyses of interiors and then mapping those transfer functions to a small anechoic room with a whole bunch of loudspeakers. And you can emulate all sorts of interiors with her technique. So please try to sign to the next one. It is a different Zoom meeting, so you have to sign out of this one, check your agenda, and sign on to the new one. And we'll be waiting for you on the other side. Thanks very much.
Stephen, sorry, can I just a quick question? I don't have I don't know if an invitation was sent to the other meeting or whether I should access it directly from the CAV website, but I don't know if it's too much of a problem sending me an invitation for the next Zoom meeting.
You know what? I'm going to leave this up on the screen, so that'll be faster. So, and I'll go ahead and send invite again as well. But here is the next meeting ID and password. And here it also is for the student poster competition. So I'll just leave that sitting up until everybody signs off so you can write it down.
Terrific. Thank you very much.